astronomical colloquium of this semester. And with great pleasure, we welcome Catherine Zucker from the Harvard Smith. Is it pronounced?
The Center for Astrophysics, PIPE, Harvard and Smithsonian.
All right.
That's the vertical.
So it's not the Harvard Smithsonian Center for Astrophysics anymore. All right. So we learned something new.
Is that no? Okay, the PIPE style. It's just pause. Yes.
All right. So she is from Harvard, and this specific institute, but I learned she's actually a state employee at the Smithsonian, a federal employee at the Smithsonian. Anyway, Catherine, you did your undergraduate in University of Virginia, then moved to the place to be, to Harvard, for the master and the dissertation, which you completed in 2020. Then after a very short stay at the place, you moved on to the other place to be, to the Space Telescope Science Institute as a Hubble Fellow. And you have been there for about 2 years. Then Harvard decided, oh, that was a big mistake to let her go, and hired her back as faculty or federal employee at the Smithsonian Institution. And you have been at this position since a year, roughly, since summer last year. And maybe I should say she got her PhD with a thesis of the title, Charting the Uncharted Milky Way. So it's a very lyrical title. And I think some of that and what has happened since we will learn today. You have many publications, you have many prizes. Maybe let me mention a few. The Bart Bock Prize Lectureship on research in the Milky Way, that is the most recent one. Of course, there is the Hubble Fellowship that you got, but there is also a Fireman Fellowship from Harvard, and you got a prize for one of the best dissertations at Harvard University, as I understand. And I forgot the name of that, right? Harvard Horizon Scholar.
So I had two. So one of them was this man right here, Doug Finkbeiner, and the other was Alyssa Goodman. Alyssa Goodman, yeah.
All right, and with that, welcome, and we are curious what we learned from you about the solar nebula.
Okay, thank you so much, Ralph, for that kind introduction. I'm very happy to be back in Heidelberg. And today I'm going to talk to you about our ongoing work to map the 3D structure and dynamics of our solar neighborhood in the Milky Way galaxy and understand what that is teaching us about star formation. But before I begin, I want to thank my many wonderful collaborators that you can see listed here, without which this work would not be possible, and some of them are in this room today. Okay, so this is the galactic baryon cycle. It describes how matter flows through different phases of the interstellar medium and also the circumgalactic medium. It's a key driver of galaxy evolution. And as you'll see, at the front and center of the galactic baryon cycle is star formation. So it's arguably the biggest insect in the galactic baryon cycle. And so what we're going to be talking about today is essentially the bottom half of the galactic baryon cycle. So essentially, we want to understand how molecular clouds form out of the turbulent diffuse interstellar medium, how those molecular clouds collapse to form stars, and as those stars evolve and the most massive of those stars explode, how do they affect further star formation in the Milky Way? So essentially, everything in yellow we'll be touching upon today. So the galactic baryon cycle is a key driver of galaxy evolution, but it's also incredibly challenging to study because the physical processes that shape it span many orders of magnitude in spatial scale. So essentially, we care about the scale of an entire galaxy, so many kiloparsecs, all the way down to individual circumstellar environs and planetary systems. And so if you do the math here, to understand the baryon cycle, we have to constrain the physics over 9 orders of magnitude in spatial scale. And so, of course, that's very challenging. And so essentially what we're going to do today is try to place some concrete constraints on the physics that is happening on each of these scales. And so, again, many orders of magnitude in spatial scale. But also the second challenge in understanding the galactic baryon cycle, one thing. So throughout the talk, you'll see all of these iconic images. So those are essentially sort of the classical picture that you see for different scales. So what a young solar cluster looks like, what a molecular cloud looks like. And so those are the most iconic images. But throughout the talk, you'll see images that look like this. So this is the actual data that we're constraining on the local Milky Way. And so we'll actually span all 9 orders of magnitude in spatial scale. So some people find this a bit jarring because we are spanning 9 orders of magnitude. But throughout the talk, you'll see these little insets. And so it'll hopefully help orient you in terms of what scale we're looking at that point. So keep these little icons in mind. You'll see them again. Okay. And the second challenge is that not only does this span many orders of magnitude, but we're actually missing a true 3D physical picture of dense gas and young stars. So essentially, when we have a simulation of a galaxy, we have 3 dimensions of space and we have 3 dimensions of velocity. But traditionally, when we study our solar neighborhood, we've only had a lower dimensional space in terms of constraining the physics. So what does that mean? So traditionally, in terms of the solar neighborhood, we've had so-called position, or plane of sky views of the interstellar medium and its young stars. And that's essentially where everything along the line of sight has been projected onto a single plane of the galaxy. That's why it's called plane of sky. And so we've either had these 2D projected views of the galaxy locally, or we've had so-called position, velocity views, where the third dimension is not the distance or the depth in true 3D space, but rather it's the radial velocity of the gas that you obtain from spectral line mapping from the Doppler effect. And so essentially what we've traditionally been able to recover is 3 of 6 dimensions. So 2 dimensions of space and 1 dimension of velocity. But what we really want to do is recover all 6 dimensions in order to understand the physics that shapes the galactic baryon cycle. And so that's exactly what we're going to do over the next 45 minutes or so. We are going to construct a multi-scale 3D physical picture of dense gas and young stars in the solar neighborhood. And so just to be very explicit here, by the end of this talk, we will have 3 dimensions of space, so x, y, z. We'll have 3 dimensions of velocity, vx, vy, vz. And if you have both of those things, you actually have a time dimension. We can actually trace the galaxy back in time and understand how star formation and the gas distribution in the solar neighborhood came to be. Okay, so just as a brief summary, you'll see this video now and you'll also see it at the end. Today, we're going to take a journey across 9 orders of magnitude in spatial scale. We're going to start at the scale of a galaxy, and we're going to zoom down into the solar neighborhood. And we're going to look at this new structure called the Radcliffe wave, which is essentially a galactic scale gas wave that defines the nearby local arm of the galaxy. Then we're going to zoom down into hundreds of parsec scales into this giant bubble that you see in purple, which has been carved out by supernova. And we're going to look for evidence of star formation on the surface in the form of this distribution of molecular clouds and young solar clusters you see here in cyan. Then we're going to zoom inside the local bubble, and we're going to go down onto parsec and AU scales. And we're actually going to look at the heliosphere around the sun. You can see here in yellow, it's a protective cocoon powered by the solar wind. And we're going to look at the effect that the sun's trajectory through the dense, cold interstellar medium of our galaxy has had on the effect of the properties of the heliosphere. And so you'll see today that we firmly lie inside this crescent, sort of croissant-shaped heliosphere. You actually see Voyager 1 lies outside of it. We'll get to that later. But essentially, we'll discuss how this model has changed over time. And then we're going to zoom back out on parsec scales, on kiloparsec scales, and we're going to look at the rest of the galaxy and figure out how we can go beyond the solar neighborhood to understand the physics of the galactic baryon cycle at large. Oh, and if you want to see the video for yourself, go to tinyurl.com/sf-across-scan for like a super high resolution view. Okay, so in our journey across 9 orders of magnitude, we're going to start at the scale of galaxies and molecular clouds. And we're going to talk about how we create these true 3-dimensional X, Y, Z views of the interstellar medium. And we do that using a technique called 3D dust mapping. So essentially, 3D dust mapping leverages the effect that dust has on stellar colors to map the distribution of the interstellar medium in 3 dimensions. A lot of the 3D dust mapping work was pioneered here, actually not here, pioneered in part by Doug Finkbinder's group, which is at Harvard, but Doug is physically here right now. So thank you, Doug. So we're just going to walk through this example. So essentially, say, for instance, we have a star in the Milky Way. That star is intrinsically green. We detect the star via various large photometric surveys in 2D on the plane of the sky. And so if there was no dust cloud between us and that star, this intrinsically green star would appear green. Makes sense. However, of course, we know that there's dust clouds scattered all throughout the Milky Way in 3 dimensions. And if there's a dust cloud between us and that star, this intrinsically green star will become reddened according to the column density of dust. It passes through along the line of sight. We can see this effect very clearly in something like B68, which is my favorite globule. You can see there's sort of a reddening effect around the edges. And so, of course, we have many stars scattered throughout this cloud in 3 spatial dimensions. And their colors will also become more or less reddened according to the column density of dust that they pass through. And so the key point here is that you can use 3D dust mapping to infer this 3rd spatial dimension of distance from dust effects on stars. So in reality, this picture is way more complicated. It takes millions of CPU hours. Not all of these stars are intrinsically green, of course. They have different stellar types. But it's in essence, 3D dust mapping simultaneously models the intrinsic colors of all those stars, the 3D distribution of dust, and the stars' distances that self-consistently produces the 2D colors of stars on the plane of the sky. And so, of course, this problem becomes a whole lot easier if you have independent constraints on the stars' distances from Gaia, which we now do. And so essentially, 3D dust mapping has undergone a revolution in the past 5 years or so, thanks to Gaia providing independent constraints on all of these stars' distances. So this is a 3D dust map from Greg Green, who is at MPIA here. So you can see this is a 3D dust map out to about 2 kiloparsecs from the sun. You can see there's a lot of structure here. The brown means there's more dust. And so we'll actually hone in on one of these regions in a second. So can we actually trust the dust? So do they provide reliable distances? So early on, we actually did compare the distances that we get for dust clouds from 3D dust mapping versus the sort of gold standard distances, the star-forming regions in the Milky Way from masers. This is Mark Reed's Bessel survey. You can see a distribution of maser properties here, top down. So each red point marks the 3D position of a massive star-forming region whose distance has been measured with trigonometric parallax. And so this is set the gold standard. And so what we find is that they do agree with the gold standard approach to within about 10%. But critically, the point I want to convey here is that 3D dust mapping can be used anywhere where there's dust and measurable stellar properties, while as the gold standard traditional approaches require spatial regions on the sky. So if you can leverage stellar colors and positions to map the dust, you can unlock a whole new volume of the galaxy to explore the 3D distribution of the ISM. Okay, so what did we learn from 3D dust mapping? So essentially what we did, myself and Josh Spiegel and many other collaborators at Harvard, we essentially used 3D dust mapping to find the distribution of all nearby star-forming molecular clouds in the solar neighborhood. So each red dot here marks a blob of star-forming gas whose distance from the sun has been measured using this 3D dust mapping technique combined with Gaia. And what we found is that these star-forming regions, these blobs of gas, dense gas, are not randomly distributed, but they form an almost 3 kiloparsec long wave of gas that undulates in and about the disk of our galaxy with an amplitude of about 160 parsecs. You can see the stats down here. It has an aspect ratio of almost 20:1 and a gas mass of more than 3 million times the mass of the sun. And so this structure is particularly striking. But the thing that people comment on the most is just how close this structure is to the sun. So at its closest point, we lie about 200 parsecs away from the so-called Radcliffe wave. If you're interested in why it's called the Radcliffe wave, I can explain later. But essentially, the question is, we've lied so close to the structure. Why did it take so long to discover it? And the answer is that we didn't have good enough distances to star-forming regions. We didn't have this critical 3rd dimension that allows us to reconstruct 3-dimensional views of the interstellar medium. So essentially, schematically, this shows sort of the typical distance uncertainties before the Gaia era of 3D dust mapping. After we added Gaia into our 3D dust mapping pipeline, those distance errors went down by essentially an order of magnitude or more, essentially overnight. And so when you have these very precise distances, the true spatial arrangement of the dense interstellar medium sort of pops out at you. This is a sort of a different projections of this new structure called the Radcliffe wave. This is a top-down view of the galaxy at left. The sun's at the center. So it's incredibly linear. So it has, again, an aspect ratio of about 20:1, top down. But critically from the side, you see it undulates like a sinusoid about the disk of the galaxy, and also connects some of the most famous dark-green regions near the sun. So many of you might have heard of regions like the Orion Nebula or the Cygnus X dark-green region. So it's connecting dark-green regions on scales that they were never previously expected to be connected so intimately on this scale. Okay, so this is a gigantic structure. It's about 3 kiloparsecs long. And so the question is, what is the relationship between this wave-like structure that we discovered with 3D dust mapping and traditional estimates of galactic structure based on these maser views of the galaxy? So essentially what I'm showing you now is all the dark-green regions along this Radcliffe wave-like structure. And then what I'm turning on in a second is our traditional model for the nearby local arm of the galaxy. So these blue dots are positions of high mass dark-green regions constrained by the Bessel survey. And then that's the log spiral thick constrained on much larger scales for the nearby local arm of the galaxy, which is the galaxy that is, which is the spiral arm that is closest to the sun in our Milky Way. And so what you see here is that if you look at the nearest spiral arm at very high spatial resolution, there's a lot of substructure. So the local arm is not what we expect it to look like locally. It's wavy from the side and very straight from top down. And so the question is, do all sort of spiral arms have this substructure? What does it mean for the formation of the wave, for the evolution of the structure, and for the evolution of spiral arms in general? So you see the Radcliffe wave is just a small piece of the larger local arm. So we're trying to push out further to see whether this structure is expected elsewhere. Okay, so we covered about kiloparsec scales and hundred of parsec scales. We've talked about 3D dust mapping and how we can reconstruct the 3D spatial distribution of the ISM. But that's only one half of the equation. And so the other half is we have to know not only where stuff is, but we have to know how stuff is moving. And in order to figure out how stuff is moving in 3 dimensions, we have to go down another 2 orders of magnitude in spatial scale to the scale of young stellar clusters. So essentially the idea here is that we can use young stars embedded in these molecular clouds to trace the 3D space motions of their parental gas. So the idea is that if you have a young star cluster embedded in a cloud, they have not strayed too far from their birthplaces. And if you compare their radial velocities, they're very similar. And so for these very young star-forming regions, you can use the clusters to understand how these clouds are moving in 3D. So this is an example. You can see right there, that's a 1 million-year-old star cluster embedded in a 3D molecular cloud. I'll talk about that in a second. And so you see that arrow is pointing to essentially the motion of that young stellar cluster through the galaxy in 3 spatial dimensions. And so if we know how that cluster is moving, we know how the parental cloud is moving as well. And so what we've done is we've taken all of these young stellar clusters in the solar neighborhood of our Milky Way. We've connected with their 3D parental molecular clouds, and we've tried to figure out how this Radcliffe wave-like structure is moving in 3 spatial dimensions. And so putting this in context, this is work that's been led by now rising second-year Harvard PhD student Ralph Konietzka. And what he did is he looked at the 3D young stellar cluster distribution along the wave, and he modeled the dynamics of the wave. And what he found is that not only does this wave-like structure look like a wave, but it also actually moves like a wave as well. So this Radcliffe wave-like structure is indeed oscillating, as one would expect. And if you actually model the specifics of the oscillation, it's actually most consistent with a traveling wave with a max vertical oscillation in the z direction perpendicular to the disk of about 14 kilometers per second. So it looks like a wave and it moves like a wave. And so just to sort of wrap up the implications on kiloparsec scales, we've essentially looked at the distribution and dynamics of dense star-forming gas. And we found that many of them are arranged in the so-called Radcliffe wave. which forms the dense part of the nearby local arm of the galaxy. So essentially, the local arm is not shaped as we thought it was locally. It's straight from top down and it's wavy from the side. We found connections between star-forming regions that were previously thought to be isolated. We find that this wave is oscillating, but the wave's origin is still unknown, and we'll have to do some detailed comparisons between the actual dynamics of the structure and predictions from numerical simulations and analytic theory. Okay, so essentially the 3D dust mapping revolution has been accelerating so quickly that in about 3 or 4 years, we've gone from being able to just find the distances of things on average in the galaxy with very high resolution to actually being able to resolve the internal structure of these clouds. So to put it briefly, we've gone from finding distances to things with 3D dust mapping to finding shapes with 3D dust mapping. And so just to give you a sense of the progression, we're going to start out here on kiloparsec scales, looking down on Greg Green's map of the galaxy, looking at the Radcliffe wave. We're going to go down into the nearest kiloparsec or so with a new map led by Gordian Edenhofer and Torsten Ensen's group, Philip Frank, myself, Andrew Sejari has been involved, Josh Spiegel in the construction of this map. And essentially what we've done is we've taken a smaller volume of the galaxy, but increased the spatial resolution. We're going to keep going down. We're going to look at map by Reimer Leica in the nearest 400 parsecs. And we're going to zoom down into the scale of an individual molecular cloud on 100 parsec scales. And you can see that we've actually been able to resolve on 1 parsec spatial resolution the internal structure of these clouds. So we've gone from just like marking the position with a red point to actually marking the internal structure of every one of these nearby star-forming regions. Okay, so let's take a look at them. So if you look at all of the nearby molecular clouds on about a few parsec to 100 parsec scales, this is what they look like. So these are all the very famous nearby star-forming regions, like the Orion Nebula, like Taurus, like Perseus. And so you can see there's a lot of very rich substructure that was invisible based on lower resolution maps. And so the 2 takeaways, and Richard Tufts will be very interested.
So just to give you some brief context on this local bubble. So we've actually known about the local bubble for about 50 years. And we've known about it as a region of lower density, of higher temperature, that's more highly ionized. And so the fact that we live inside a bubble is not new knowledge. But what is new is the fact that all of these nearby star-forming regions lie on the surface of this bubble. So just to give you a connection to sort of the star formation across scales theme, this local bubble is responsible for some of the prettiest pictures in the field. So if you zoomed in by a factor of 10 on this Ophiuchus star-forming region, you would see this beautiful Rho Ophiuchus nebula. And if you zoomed in on the other side of the bubble by a factor of 10,000, you would see this famous disk called HL Tau observed with ALMA. And so again, on very large scales, the formation of structure can cascade down to smaller scales. Okay, so what have we learned about the local bubble? So there's 2 things. So one, I mentioned that we can use the motions of young stellar clusters to trace the motion of their parental gas clouds. And so we did this not just for the Radcliffe wave, but also for the local bubble. And so this is a top-down view of the local. Okay, I think we're, yeah, okay, all good. This is a top-down view of the local bubble on the left. So again, we lie at the center. And then you'll see all these squiggly colored lines of the positions of nearby molecular clouds. And all those arrows are showing how their young stellar clusters are moving in 3 spatial dimensions. And so you'll see that not only do all these star-forming regions lie on the surface of the bubble with morphologies consistent with being compressed, but their young stellar clusters all point away from the bubble center of expansion, which is clear evidence that they've potentially been swept up over time as the supernova have carved out this cavity. And then the second is that this local bubble is intimately connected to its larger scale environments. You actually see it's expanding into the Radcliffe wave on one side. And so there is an intimate connection between supernova feedback on bubble scales and spiral structure on larger scales. We will talk about that. We will talk about how the sun got there. We will talk about why this shouldn't make you deeply uncomfortable. You just have to wait like 15 more minutes. Is that okay? Okay, perfect. Perfect. Okay, so we have the 3D positions and we have the motions of all of these molecular clouds and their young clusters. And so with those two things, we can actually go back in time and reconstruct the history of star formation in our solar neighborhood. And what we found is that about 14 million years ago, a series of supernovae started exploding. So we think that roughly 15 have exploded over the past 14 million years. And essentially, this supernova carved out this cavity and led to the formation of this expanding dense shell, parts of which have become so dense that they've fragmented and collapsed and produced these expanding sort of surface of young star formation all around us. And so that was the cartoon. But on the right-hand side, we actually have the real data. And so you'll see over time, as this bubble expands, you'll see little like dots of points appear. That is where we predict that young star formation is happening on the surface of this expanding sphere. Models a very simplistic sphere over time due to the so-called sort of supernova-driven star formation scenario. Okay, so this is essentially a top-down snapshot of frame by frame over time of the movie I just showed. So in the top panel here, 16 million years ago, we're essentially saying that there wasn't too many supernova going on. It was mostly that's sort of when our video begins. And then a couple mega years later, we have these two massive star clusters forming. And those massive star clusters are going to start producing supernova that are start blowing out a bubble. And then you'll see epochs of star formation happening around 10 million years ago, 6 million years ago, and 2 million years ago. And in the present day, we'll see this full bubble in all of its glory with all the star formation on the surface and all of its young stars moving away from the center of expansion. Okay, so one thing that's really cool about studying the solar neighborhood is that we have a lot more information locally than we have extragalactically. And so we actually think we know the massive clusters that had massive stars in the past that went supernova and carved out the expansion of this bubble. And so we actually think we know the stellar populations that led to the formation of this bubble. So for the purposes of this talk, they're called progenitor cluster 1 and progenitor cluster 2. It's part of the Scorpius-Centaurus OB association. It's a very famous OB association if you're into OB associations. But essentially in the present day, they lie near the edge of the bubble. Their positions are marked with the green arrow. But if you trace them back in time, they lie exactly at the center of the bubble where it would have started to form. And what's really cool is that if you look at the remaining stellar memberships of these clusters and you model how many essentially stars are missing, you find that these two massive clusters have produced roughly 14 to 20 supernova over the past 15 million years or so. And if you actually look at the current properties of the shell and the total momentum in the shell, how much momentum would have needed to be injected by supernova, you find that about 15 supernova would have needed to power the expansion of the and so we think we actually have smoking gun stellar populations that are responsible for the formation of the local bubble. Okay, so let's put it in the galactic context for real, extragalactic context for real. So I think most of you hopefully have seen this image before. Has anyone seen this? Audience participation? Okay, perfect. Okay, so this is a view of a nearby galaxy called NG. Oh yeah, this is like the FANGS collaboration, like part of them are here. Okay, so you've probably all seen this. Anyways, so this is a view of a nearby galaxy observed with the FANGS survey, the FANGS JWST survey, NGC 628. And so you can see all of these bubbles in this galaxy. And so I want to zoom in on one bubble that I love because it's particularly local bubble-like. So essentially that bubble right here is essentially exactly the same size as the local bubble. So putting it in context. So that's just one bubble from the NGC 628 galaxy in comparison to the local bubble. You can see the scale bar of about 200 parsecs there. You can see there's potentially evidence of young star formation on the surface of this bubble as well. And so what I really want to emphasize and what's really cool about the solar neighborhood is that the solar neighborhood is the only place in the entire universe where you can produce these 60 models of the ISM and young stars. So 3 dimensions of space and 3 dimensions of velocity. So we can reproduce these really detailed case studies. But then extragalactic context, it allows you to get a very statistical view of star formation. And so if we can combine in the future galactic and extragalactic star formation studies, we can understand the baryon cycle in much greater detail. Okay, so it would be very strange if the local bubble was the only bubble near the sun. So fortunately, it's not. So we live in a very bubbly medium, just like we see in the nearby Fangs galaxies. And so first-year PhD student Theo O'Neill has actually been working on extracting the full diversity of bubbles in highly resolved 3D dust maps. And this is their results. So the local bubble is shown here in the center. And then all the other bubbles that we've begun to extract are shown in cyan and blue. And then all of the molecular clouds are shown in pink. And so in many cases, we do see molecular clouds lie on the surface of other bubbles. And so the idea here is that if there's bubbles everywhere, the likelihood that you're going to be inside a bubble is statistically very high. So if you moved yourself like a kiloparsec to the left or a kiloparsec to the right, you'd also likely lie in a bubble. And so it's not too strange that we live near the center of one. Okay, so implications on scales of molecular clouds and young stellar clusters. So essentially, we can reconstruct the history of star formation in our solar neighborhood over the past 20 million years or so. And we find new constraints on the 3D spatial structure of nearby molecular clouds and find a lot of them have sheet-like and filamentary morphologies consistent with being shaped by supernova feedback. We find that most nearby young stars lie on the surface of the local bubble and their motions are away from the center of the bubble's expansion. We think we find a self-consistent explanation for the origin of nearby star formation, and that this large-scale gas compression driven by supernova may be a primary cloud formation mechanism. And finally, the local bubble is one of many bubbles in the solar neighborhood. And so one of the goals in the future is to understand how these bubbles interact to regulate star formation near the sun. Okay, so going back to your question, how did the sun wind up in the bubble? So one thing that's really cool is that if you have a model for how the bubble expanded and you can trace the sun back in time, you can actually figure out when the sun crossed through the shell of the local bubble. And so we find that the sun was actually over 300 parsecs away when the bubble first started forming. So it's over there. And so we're going to move time forward. And then you'll see that about 6 million years ago, we crossed through the shell of the local bubble. And so it's just in the present day that we happen to lie near the bubble center. So this is a relatively recent phenomenon. And so the question that we all want answered is, what does the sun's time crossing the bubble mean for us here on Earth? And so in order to answer that question, we have to go down a few additional orders of magnitude in spatial scale to the scale of circumstellar environs and planetary systems. We have to go down to AU scales. And so essentially, we think that the sun's trajectory through the interstellar medium and the sun's time crossing the surface of the local bubble actually could have an effect on the properties of the heliosphere, that yellow croissant-shaped model I showed you at the beginning. And we think that essentially when you cross through a dense cloud, you can actually shrink the heliosphere and expose Earth to the cold, dense interstellar medium. So this is a model for the heliosphere in the present day on the left-hand side. So you can see the solar system is firmly inside, the entire solar system is firmly inside the heliosphere. But you actually see that Voyager 1 and Voyager 2 have actually left the heliosphere. They're actually in interstellar space at the moment. You saw that at the movie at the very beginning. And we actually care whether one is inside or outside the heliosphere for a number of reasons. But in one instance, we care because the heliosphere actually shields us from low energy cosmic rays. And so you'll see this is Voyager 1 measurement of the cosmic ray influx that it feels as a function of time. And you'll see that as soon as Voyager 1 has crossed the boundary of the heliosphere, that the cosmic rays have jumped up. And so you can imagine that we want to understand the evolution of the heliosphere over time in order to understand its effects on life here on Earth. Okay, so for the past few years, I've been working with Merav Ofer and collaborators at Boston University to connect our new models for the sun's trajectory through the interstellar medium with implications for that, the effects of dense clouds on the heliosphere. And so essentially what we think happens is that 6 million years ago, the sun crossed the local bubble boundary. And by passing through a dense cloud, you can actually shrink it due to ram pressure to actually less than 1 AU in size. So this is a simulation that Merav Ofer has run, showing what the heliosphere could have looked like around 6 million years ago. And so you see it has this sort of long comet-like tail. And I've shown here the orbits of Earth and of Mars. And you'll see that, at least according to Merav Ofer's simulations, that 6 million years ago, it shrunk to about, the heliosphere shrunk to about 0.7 AU in size. And so if that's true, then half the year, roughly half the year, the Earth would be outside the heliosphere and half the year would be inside. And so all the planets except for Mercury and Venus would have been exposed to the dense cold interstellar medium, in theory. And so the question is, what does the sun's time crossing the bubble mean for Earth? And we think that this timeline of the sun crossing the heliosphere, the sun crossing the local bubble shell and shrinking the heliosphere, could be consistent with supernova iron deposits in the Earth's crust. So the idea is that if you expose the Earth to the dense cold interstellar medium, it's easier to deposit iron-60 that's associated with these small dust grains in the ISM. And so you would expect peaks in the geological record associated with various tracers. And one of these tracers is called iron-60, which is predominantly produced in supernova explosions. It has a half-life of roughly 2.1 million years. We see it all over. So we see it in deep ocean samples. We see it in Antarctica. We see it on the moon. And so what I'm showing of the influx of iron-60 atoms here on iron-21. And you'll see that there's essentially two peaks in the iron-60, one around 2 or 3 million years, 6 million years ago. And so we think it's possible that the one about 6 million years ago could have corresponded with the sun crossing through the local bubble shell, the heliosphere shrinking to the contact with dense clouds, and allowing more iron-60 produced in the local bubble supernova explosion to be deposited here on Earth. There's definitely alternative theories. There's also theories that you can interact with the supernova blast wave directly and cause these. Only a really interesting hypothesis that hopefully we can follow up on in the future. Okay, so on AU scales, the implication is that the sun's trajectory through the ISM over the past 10 million years shaped the properties of the heliosphere potentially. Sounds good? So we find that the sun crossed the local bubble shell around 6 million years ago, and we only happen to lie near the bubble center in the present day. Okay, so so the implications on AU scales is that the sun's trajectory through the interstellar medium could affect the properties of the heliosphere and allow it to evolve over time as a function of essentially galactic weather, so how the sun moves through dense clouds in the Milky Way. So we find that we crossed the sun crossed the local bubble shell around 6 million years ago. This crossing may have shrunk the heliosphere, according to Merav Ofer's simulations, and potentially exposed the Earth to the dense cold interstellar medium. This crossing time could be consistent with the geological record and this influx of supernova iron isotopes here on Earth. Okay, so today, in the last 40 minutes or so, hopefully you followed along as we took this journey across 9 orders of magnitude in spatial scale. And I've convinced you that star formation is mediated by physical processes that happen over many orders of magnitude in spatial scale and in time scale. But what I want to leave you with is that we've only really looked at a tiny fraction of the galaxy. So you can see here, this is a top-down view of the current reliable 3D dust map at high resolution in the context of the full Milky Way. And you'll see, again, we're missing influenced active spiral arms in the inner galaxy, very quiescent regions in the far outer galaxy. You really want to understand star formation, essentially the. And so in order to do that, we need to take full advantage of next generation infrared surveys, which will open up more of the Milky Way. So just to give you a sense of sort of the progression, I'm currently involved with the SDSS-V and Milky Way Mapper survey. There's lots of involvement here at MPIA as well as full members. And so the dust working group of SDSS-V is working on expanding our reach out to about 5 kiloparsecs from the sun. And we're trying to trace gas flows and the properties of the dust on much larger scales in the Milky Way. So that'll push us out a little bit farther. Myself and collaborators, notably Andrew Sagery. Where are you? He's in the room. Andrew right here, along with Josh Spiegel, and again, many others here at Heidelberg, are working on incorporating new infrared surveys and optical surveys, including the DCAP survey, photometry for billions of stars in the galaxy to push out to 8 kiloparsecs and reveal more environments in the Milky Way. But ultimately, what I'm personally most excited about is a combination of Roman and LSST, which could provide infrared photometry. It's also an option, but also potentially, depending on the final survey, it could also. And so just to give you a sense of how exciting this is, the Roman Galactic Plane Survey, which has been approved by NASA just within the last 6 months. This is showing point source sensitivity versus wavelength for various infrared surveys. And the Roman Galactic Plane Survey is right at the bottom there, so it's incredibly sensitive. And what I'm showing you now is the spectrum for a 1 solar luminosity embedded protostar, so a sun-like star at a distance of 12 kiloparsecs from the sun. And so what that means is that Roman could detect a young solar object on the other side, potentially of the galactic center. So it's really exciting for understanding star formation in much broader environments across the galactic disk. Okay, so wrapping up, today we have gone on a journey across 9 orders of magnitude in spatial scale. We've started at the scale of the Milky Way, and we've zoomed down into the solar neighborhood and looked at the discovery of this galactic scale gas wave called the Radcliffe wave, which is oscillating about the disk and also defines the dense spine of the nearby local arm of the galaxy. We've zoomed into a section of the wave and looked at how there is a bubble that's essentially expanding into this Radcliffe wave driven by supernova. We see evidence for star formation all along the surface of this bubble. And then we've zoomed in to the bubble down to AU scales. And we've looked at how the sun's trajectory through the interstellar medium crossing this bubble 6 million years ago has potentially affected the properties of the heliosphere that you see here in yellow. Again, this is the heliosphere in the present day, but this is potentially not the heliosphere of 6 million years ago. And so we've looked at how galactic weather could potentially affect life here on Earth. And then we've zoomed back out from AU scales to parsec scales to kiloparsec scales. And we've looked a little bit about what the new surveys are on the horizon and how we'll be able to push way beyond the solar neighborhood and understand how star formation proceeds across the Milky Way's disk at large. And so we've looked at the solar neighborhood, but the full 60 Milky Way is hopefully coming in the next decade or two. And with that, I will leave you with my conclusions and welcome any questions. Thank you.
Thank you very much, Catherine. I think we've got a very interesting set of data here, unique in the whole universe. I'll open the questions to the floor, and please, if anyone wants to start, maybe a student wants to start with the first question. Anybody wants to go? Not at the moment. Then I'll ask, I think there's a question here. Hans Walter.
I shall. So wonderful stuff. I had a question about the implication of the fact that all these young clusters lie on the shell of the bubble. There's this whole story that feedback may trigger star formation and hinder it, etc. Does that mean that most of the star formation within a few hundred parsecs of us is triggered by this particular event? And how much are you willing to generalize that to the Milky Way disk as a whole?
Yeah, so there's like multiple ways to answer this question, and it depends on whether you ask a theorist or an observer. So we definitely think that star formation, these supernova are shaping essentially the spatial, dynamical, and temporal sort of distribution of young stellar clusters. And so it's definitely compressing the gas, it's driving cloud formation, those clouds are collapsing to form stars. And so in general, you definitely see star formation preferentially happening on the edge of bubbles, because that's where the dense gas is. There's larger questions of whether supernova ultimately have a positive or negative effects on the star formation rate of galaxies. In general, if you look at galaxies like from the FANG survey, you find that if you, or in simulations, you find that in general supernova feedback lowers the star formation rates. And so whether it's actually making having a net positive effect is sort of unclear, but it's definitely shaping how we see the spatial, dynamical, and temporal arrangements of young stars, and leading to the distributions we observe. And so it's definitely organized by star formation. Whether it's triggered is more of a tricky question.
Okay. Ralph.
Great talk, Catherine. I'm wondering about the specific detail of the model, namely that the sun has been entering the local bubble about 6 million years ago, and hence it must travel with a relative speed to, the neighborhood with 20-25 kilometers per second. That seems a bit much. And so I'm wondering what you make out of that timing of events.
So your question is the relative velocity that you need to shrink the heliosphere, or what's your exact question? Yeah, correct. Correct. Yeah. 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 So are you asking why the sun's traveling so quickly? Yes, that is a great question. I think Hans Walter is probably more, no, you're not gonna be able to answer this question. I actually don't know if the sun is peculiarly fast. It is traveling. All of this is with respect to the local standard of rest. So if you just average all of the stars, we are traveling like, yeah. Yeah, and so one of the really cool questions to think about is that how a star will interact with its interstellar environment will depend a lot on the orbit it's on. It'll depend a lot on, it'll depend a lot on its orbit it's on. It'll depend like whether you can shrink like a heliosphere or around other stars are called astrospheres. That will depend a lot on the spectral type of the star. And so trying to understand how stars of different ages, of different spectral types affects like how their astrospheres will shrink and grow over time as they interact with the interstellar medium is a really cool question. One that we're just starting to answer very, very recently, but I think will become more interesting in the next 10 or 20 years.
So Hans Zinneke has traveled a long way to answer his question.
Thank you. Great to be here in person, not only on the internet. Well, first of all, I think the sun's velocity is not so high for, as Hans Walter said, for the age, because there's what's called the Spitze-Schwarzschild mechanism, which accelerates clouds or stars over time in the galaxy. Go back to Whelan. It seems normal, but my question was different. My question was about the heliosphere, and you said you see the spike rising up in the shielding or in the lack of shielding, but it's not so much either. It's factor of 2. That doesn't make a big difference. In terms of protection, it's nothing. Oh, sorry.
Sorry.
Yeah, so essentially the interesting question here, so I showed the cosmic rays because it's a very like pictorial description of having some effect of what we potentially experience here on Earth. I think the more interesting question is that there's some really detailed modeling of the effect that if dust settles over the atmosphere, essentially the effect that that can have on cooling here on Earth. And so if you can model the effect of sort of being exposed to the dense cold interstellar medium to atmospheric temperature, which you can then relate to ocean temperatures, is what we directly probe, you could essentially correlate with models for climates. So I think that's the more interesting question, is climate models, but I just showed the cosmic rays because it's the easiest one to visualize. But yeah, 75% is not a lot, but it's still, I think, a really cool diagram.
Okay, I'm done.
Okay, so cosmic rays are important for climate, I think. Next question from the back here.
Hey, thanks for the great talk. Regarding the oscillating Redcliffe wave, are there any ideas or any methods that would enable us to recognize such structures in other areas of the galaxy to find out if this is something special that happens near the sun, or if this is, happens everywhere in the galaxy?
Yeah, so that's a great question. So just based on similar arguments for the local bubble, like it's very unlikely, statistically speaking, that we're going to lie next to this only sort of undulating wave in the galaxy. We don't have the resolution currently to look at these structures beyond the solar neighborhood. If you look at the disks of nearby edge-on spiral galaxies, you do see undulations in the disks with similar amplitudes and periods, or amplitudes and wavelengths. And so that sort of wavy structure is not uncommon. We think it's likely, at least I think it's unlikely that it's like, so there's essentially processes that could arise both internally to the disk and externally to the disk. So internal processes are things like spiral shocks or supernova feedback. External processes are things like perturbers coming in and sort of shaking up the whole disk. So we're still trying to explore those two scenarios. I think it's probably more likely due to internal processes driven by a combination of supernova feedback and galactic dynamics, just because we actually don't see the same signatures in old stars as you would expect based on a perturber. But we think these should be very common, and we should find them as we push out at high resolution across the disk.
Henrik?
Thank you, Catherine. Just a question to the many bubbles you showed from Theo's work. So, or two related, how small are they? And then on the other side, a little bit, this image looked almost randomly distributed. How reliable are all these bubbles? Or is there still some, some error bars which we haven't fully understood?
Yeah, so really what I shouldn't have called them bubbles. Theo would prefer I call them voids. So essentially, we don't know whether all of those cavities are driven by feedback, and it's likely some of them are just spurious underdensities and not actually carved out by supernova. And so one of the sort of the big goals that Theo will in part be working on in the next couple of years is trying to correlate these cavities that we observe with other tracers of feedback. So like young massive clusters or H alpha emission. And so some of these bubbles or cavities or voids are definitely spurious. And so picking out which ones are like true bubbles and which ones are just sort of random voids in the interstellar medium is to be determined. There is definitely a minimum size set by our 3D dust resolution. There's a size below which we can't resolve. So we're not looking at stellar wind blown bubbles, for instance. And so it's under active investigation. Yeah.
Okay, I think we've now got just past the half hour, so there's time for one last question of the semester. And that would be Yufeng Wong.
Thanks for a great talk. From the morphology of the local bubble, is it possible for us to know the nearest and the most recent supernova explosion from the sun?
Okay, just going from the top to the bottom so that Catherine can answer.
Yes, so We do know the most recent so it depends obviously on what scale you're looking at. But we think the most recent supernova that powered the local bubbles expansion, it went off between 1 and 2 million years ago at a distance about 100 parsecs. And so there's a whole other paper that I'm working on with Seth Redfield and Ralph Konietzko and Sarah Starczewski and Jeff Linsky. Sorry, that's the full author list. I won't keep going. Talking about how this most recent supernova has actually shaped the very, very, very local interstellar medium within like a few parsecs of the sun. I didn't get to talk about that. But essentially 1 million years ago, about 100 parsecs away. I don't know, does anyone know a star named Antares? It's like a very famous star. That's probably the next supernova that will go off and power the expansion of the bubble. But we're probably fine because we're far enough away and it won't extinguish all life on Earth. So it's great.
Okay, well, I think we'll have to gradually start drawing to a close. Before we thank Catherine, a number of announcements to make. And first and most important, I'd like to thank everybody who has made this colloquium series possible, most particularly the speakers, who I think we've been treated to a very large dynamic range in topics, but all at a very high level of comprehension for us, even when we're not actually working in those fields, so we can actually understand what's happening at the cutting edge. And so I'd like to thank here all the speakers on behalf of the community here for the effort they've put into preparing their colloquia and coming here to talk to us. And if we go back to I'd like to also thank Barbara Wright at the Landessternwarte, who has been responsible for all the organizational travel and all the paperwork which goes on behind the scenes to make this colloquium series possible. So thank you very much, Barbara. And I'd also like to thank Nabanal Saha, if you could just stand up at the back, who's been on hand to deal with various little emergencies with the technical things here, but also has responsible for the recording of the colloquia. And if you want to go back and see the whole series, please go to the YouTube travel, the HJC YouTube channel. It just remains for me to say tonight, I think there may be a dinner, is that right? Wait a minute, maybe you want to talk in this.
So before the dinner, we will be meeting for drinks with Catherine at the Neuenhammer Marktplatz, because it's raining. Otherwise, we would have gone to the Neckar, to the beer garden there. And then we go to Urban Kitchen at 7 o'clock. Unfortunately, Hans im Glück was not available. It was completely booked. So Urban Kitchen at Poststraße this way at 7 o'clock.
Okay, thank you very much. Okay, so that's something to look forward to tonight. They've got some umbrellas out. You can still sit outside Urban Kitchen under the nice umbrellas there. So you know, it's not too close inside. So, 22nd of October this year will be the next HJC. We look forward to seeing you all then. And in the meantime, I want to thank Catherine for this exciting talk and all this wonderful new information we've got about our immediate local in the galaxy. Thank you very much, Catherine.